Welcome everyone to another Wireless Works webcast sponsored by Cambium Networks. My name is Daran Hermans. I'm your host today, and we are very fortunate to have back with us again. We got him tagged for three in a row, three webcasts talking about Wi-Fi 6E. One of the internal experts, wireless experts at Cambium. Cambium Networks, does so many different things, and we need people to have a broad range of wireless expertise. Mitch Parsons, why don't you go ahead and introduce yourself and tell us what you do at Cambium Networks?
Thank you, Daran. Yeah, Daran said who I was. Mitch Parsons. I'm a technical product manager here at Cambium, which means that I have to be able to understand all of our products, whether it be the 28 gigahertz that we're using for 5G, or 60 gigahertz CN wave, which we're creating mesh networks and providing internet to our point-to-point equipment, our PTP 600X and 700, as well as our Wi-Fi and our switching. So, I have to run all of them.
Well, we're very glad to have you take some time out and talk to us about Wi-Fi. Mitch, what's been your experience with Wi-Fi? I mean, how many years have you been doing that?
Well, since about the BG standard, or B standard, way back then. So I'm kind of showing my age a little bit, long in the tooth.
Yeah. Well, that goes back. Yeah, it goes back a good 20 plus years then.
Yes.
And in fact, it's interesting is in my history, I worked for Motorola, which I had bought a company called Symbol Technologies, and Motorola and Symbol were at the forefront of 802.11 technology. In fact, Symbol, the company doesn't exist anymore. It's been off for many years, but I think it was 1995. They introduced 802.11, even before they put the alphabet soups at the end of it. Brand new technology, really cool stuff. Back in those days, we used to talk about wireless as an extension of a wired network. You say, I have a network. And when people said I'm building a network, the assumption was Ethernet. Well, eventually it was Ethernet, but for time there was, what is it, token ring? No, not token ring.
Ethernet. Oh, we talk about copper and vampire taps,
yeah.
10 base T stuff.
Yeah. But it was
now
all
I'm really
wired.
showing my age. Now I'm really showing my age.
There you go. But that was all wired back in those, right? You said I'm building a network. The assumption was something wired. When we talk about wireless, there's a phrase that goes around called something like, if it can be done with wireless, it will be done with wireless. And that's the way things are today, right? We don't talk about wired networks primarily today. We always talk about wireless because that's the technology that gives us mobility and allows us to be more flexible, speeds up our deployments of networks, speeds up everything we do with that network. So if it can be done with wireless, it will. How do we make that a reality? Well, we make that a reality by dramatically improving the performance, the reliability, and the efficiencies of wireless networks. And that's where we're at today. So now we have 802.11ax. We have Wi-Fi 6E. Wi-Fi 6E is 802.11ax protocol running in the 6 gigahertz band. So that is a very, very key statement, because the 802.11ax protocol also runs in the 5 gigahertz band and the 2.4 gigahertz band. In that case, it's called Wi-Fi 6. So now this one protocol operates in 2.4, 5 gigahertz, and 6 gigahertz. But we're going to focus more on that third piece today. We're going to be talking about Wi-Fi 6E, which is 802.11ax running in the 6 gigahertz band. Okay, that's our introduction, Mitch. And so we have talked previously, this review, we talked about 3 classes of wireless networks defined for Wi-Fi 6E. We talked about VLP, very low power, 14 dBm. We talked about LPI, low power indoor, which is up to 30 dBm if you can get a 320 megahertz band channel width. And we talked about standard power, or SP class. And the SP class allows up to 36 dBm total transmit power, EIRP. So that's something we're very familiar with, but requires the access points and that network to be under control of an AFC system, an automatic frequency control system. So it's an external management entity that tells your SP network what frequencies it can use and how much power it can transmit. So there's that third party thing. So because that third party AFC system is involved there, many people are looking at LPI to be the standard technology. Let's drill into that. Actually, you know what? I got to ask you, because I'm kind of wondering this myself as I was preparing for this webcast. I'm looking at these classes, VLP 14 dBm max, and it's not really germane to our conversation, but I got to ask you, what the heck are they thinking? What good is What good is 14 dBm? Because I can't figure out the use case.
That's a good question, but I mean, scratching my head, thinking like an engineer and having a really awesome sound system in my house, I start thinking, if I had that low power thing with that 6 gigahertz, my DVD player could talk to my TV and I wouldn't need that HDMI cable. And then my remote speakers, I wouldn't have to get up in my attic and run cables over from my receiver over to the speaker sets and everything like that. So I mean, this allows, the average day user just to kind of set some things up and not necessarily have to have some of those specialized skills of being able to saw on the wall and, put in bring the wires down and all this other stuff. So, I mean, it's just if I got power to it, which, in this day and age, battery works just fine. And one of the capabilities of the Wi-Fi 6 itself is only waking up when I need to be spoken to. So it's going to have that reduced power capability. I mean, it really looks, to be utilized in, the IoT market. I mean, that's what I'm really going to kind of break that down to.
Interesting. You brought up a couple of good things to think about. I'll give some thought to those. But interesting about what your comment there, Mitch. You're talking again about devices and applications driving the network topology. And that's actually been true for many years. We just look back the last 10 years. Let's just go back 10 years. We can go back 20, but let's look at the past 10 years. So this is 2021. Go back 10 years ago, 2011, we were 6 months at this point. Well, actually go back 11 years. So by the middle of 2010, May 2010, Apple introduced the iPad. And quite frankly, turned the world on its head. They kind of expected Apple would do it. Nobody expected it would take off as quickly as it did, which became super popular. Tablets became all the rage. Tablets everywhere really changed the density. Not only tablets, the timing was really right because smartphones by 2010 were taking off rapidly. The growth rate of cell phone adoption, smartphone adoption was just growing every year, leaps and bounds. So some markets really changed dramatically. For example, hospitality. I was been involved in that for a lot of years. Between 2010 and 2012, just in about an 18 to 24 month period of time, the networks increased over 2 times density and over 2x the number of devices, active devices in an average hotel over a period of about 18 months. And then the next 18 months, they doubled again. So there was this dramatic increase in the numbers of devices that are being used. And that really did change the way networks were designed. So I'll use hospitality as an example again, and very similar to other types of MDU applications like healthcare or long-term care facilities. When the client density increases that much, and they're starting to do more with it, like streaming multimedia, streaming media, watching movies and things, what happens is your AP and clients, the AP cell sizes have to shrink. They have to get smaller. And that actually happened in hospitality. You go back 2010, we were still deploying networks in the hallway, on the ceiling of the hallway, roughly 1 for every 8 rooms. But that very, very quickly started to fail as smartphones and tablets with their smaller transmit power really took over the market in 2010, 2011, 2012. So by 2012, that 1 to 8 ratio was down to 1 to 5. Another year, it was down to 1 to 4. And then all of a sudden, the wall plate APs, people realized, wait a minute, we should be doing this with a wall plate AP, which actually were available in 2009, 2008, but they weren't that popular until the density drove the requirement. So by 2014, 15, 16, you're starting to see wall plate APs dominant in these MDU type applications, starting out with 1 wall plate for every 3 rooms. Then it was 1 to 2. By 2018, there's one wall plate access point in every single room, again, driven by the client devices and the applications in order to support the streaming multimedia, in order to support the low power smartphones and tablets and their lower transmit powers and their battery operation, and to be able to maximize their batteries, really drove that size of those wireless cells to be very, very small. So that has been something that we've all had to deal with. How about you? What do you? Is there any markets that you think of where the applications and the client devices have driven the technology changes and the network design?
Yeah, I mean, you brought up the medical field, right? I mean, a lot of their stuff, they do RFD tagging to know where it's at. They tag their people to know where their people are at for safety reasons. And I mean, a lot of that stuff is coming across Wi-Fi devices that are sharing that Bluetooth capability is for knowing where location where people are. And we'll even take a recent example. Whenever COVID came out, Wi-Fi was being utilized for that to be able to do contact tracing. So, I mean, those cell size are really important because, if I get a wide cell size, well, I'm not going to really be able to track that device as accurately as if I can make that cell size start being smaller, right? So, I mean, just for the pure fact of being able to do contact tracing, knowing where my equipment's at through RFD tagging. Education does kind of the same thing, right? Where now they're putting a bunch of tablets in the hands of students instead of spending the money on books. And so there's there's really about an AP per classroom now. I
Yeah.
mean, it was kind of the same thing as the hotels and everything else where, you kind of put an AP out in the hall, and you're kind of expecting some coverage, or maybe every other room, kind of start changing every other room. And, then, we've had also kinds of designs for multi floored places where sometimes you skipped a whole floor because of the way that you did your density for your channel reuse. But you're right. Now it's like, okay, we're down to what almost you could say is a picocell in the sense of what we do to deliver to our clients.
Good. Yeah, good. All driven by the device types and the applications. So now let's talk about how this is going to map into Wi-Fi 6E. So we have the three classes. We talked about VLP. The next one is LPI, low power indoor. Now, low power indoor is very interesting. It really maps quite well into this discussion that we're having about how the network topology has changed. So with LPI, we're starting at they've lowered the PSD, the power spectral density, is for LPI is 5 dBm per megahertz, 5 dBm per megahertz. So if we do the math on that, and honestly, we don't think about dBms per megahertz when deploying Wi-Fi networks. We tend to think of things in terms of RSSI measurements. So we think of dBm. We talk about the noise floor in dB. We talk about the signal to noise ratio in dB. So those are the terms that we're familiar with when we do network topology. So let's convert that 5 dBm per megahertz, and let's see if we can work this into something we're very familiar with. So with LPI, that 5 dBm per megahertz translates into, mathematically, on a 20 megahertz channel, it mathematically calculates to be 18 dBm. So that's a number we're familiar with, 18 dBm. That's going to be the allowed power level for LPI. So that doesn't sound like a lot. And particularly when you think about, I used to, most APs that I deploy these days are 30 dBm, 27, 30, 32, 33 dBm, something like that. 18 sounds like a very low number. But as we were just talking about, the changes in the applications and the clients are driving the cell sizes smaller anyway. Now let's talk about LPI. As we're driving that cell size smaller, another thing we want to do oftentimes is we want to increase the channel width. We want to go from a 20 megahertz channel to a 40. So what happens, Mitch, in an LPI class network for Wi-Fi 6E, what happens when we go from a 20 megahertz channel to a 40 megahertz channel?
Well, so first off, when you go to that higher channel, my noise floor level has to come up. So I don't have as much SNR to play with, right? I can't be down there my 80 to 90. I've got to come up, somewhere lower than that. Usually it's about a 3 dB. right? 3 dB loss whenever I go up in that channel size. But you talked about that megahertz per dBm, right? So now since I've went up in channel size, I also gain back that 3 dBm in power. So I'm making up for my loss with my gain. So it's a zero-sum trade.
Okay, so because we just doubled, right? You went from 20
Just
megahertz
doubled, yes.
to
Yep.
40 megahertz. We just doubled the width, and therefore the maximum allowed transmit.
We doubled the power. We allowed 3 dB double power.
Which is 3 dB. Good. So that
Right.
offsets. So the noise floor went up by 3,
Right.
and the power level went up by 3.
So zero-sum game. We basically had the same SNR to play with, where we would not have had before.
Okay, so going from 20 to 40, we've doubled our speed,
right?
And we kept the SNR the same.
Same,
That sounds
exactly.
good. What happens when we go to 80?
Well, we get to double again. We doubled the bandwidth, right? We
Okay.
get to double the power, another 3 dB. We did lose 3 dB again for our SNR from our noise flow level, right? But we gain 3 dB in power. So again, another zero-sum change. So the SNR gets to stay the same as I move up in my bandwidth.
All right. So if we add this up, we start at 18. We go to 40. We go a plus 3. So 18 plus 3 is 21.
Yep.
And then 40 to 80, we doubled it again. That's our second doubling.
We're about 24. Yep.
Now we're at 24.
Yep.
But the standard now, the Wi-Fi 6E standard allows 160. So there's a third step. So
Right.
160 megahertz wide channel. So do we double again?
We double again. That's the great thing about this, right? We just keep doubling.
Okay, so now we're up to 27 dBm total
Yep.
power, total transmit power, and our noise floor has also gone up by the same 3, 6, 9. It's now gone up by the
Right.
same number. So
Yep.
we have the same exact SNR on a 160 megahertz channel as we have on a 20 megahertz channel.
So
right?
we lost nothing. Yeah, we lost
Did I get
nothing.
that
We got all the gains as we were going up just by increasing our power.
Okay, good. So we have a constant SNR with LPI. I think that I like that because that really plays well into the planning for these high density networks. It allows us to design that network then to get to that 30 dBm SNR consistently across all the APs or all the devices that are within that cell, have that constant high signal to noise ratio, and then just adjust the channel width according to the frequencies that we have available. And here's the good thing with Wi-Fi 6E, I'll put you on the spot here. How many 160 megahertz channels do we have available across 1200 megahertz? How many do we have?
Roughly about 15 to 16 channels available.
It's a lot.
That is a lot compared to what we used to have, only 2.
It's a significant number. So we can certainly see a big increase in these larger cell sizes with Wi-Fi 6E because we have the spectrum to spare, and because the signal to noise ratio is the same between a 20 megahertz and a 160 megahertz channel. That's really good. That's on the positive news. Now on the negative side of that, it does mean that those cell sizes are going to be smaller. So how does that change sort of the way the way you think about it? Can you lick your finger and see which way the wind is blowing? Is that going to work for a Wi-Fi deployment?
That was good for B, G, and A, but no, we got to do a little bit better, right?
Okay.
So we're going to have to use some of our propagation equipment, prediction stuff, and then we're going to roughly have to look at more AP deployments, deploy more APs to be able to provide that same overlap and coverage.
Okay, good. So it will change, but fortunately the tools that we have available, both predictive RF planning tools that are commercially available, even the one that Cambium puts out, makes it available to our partners. It's a web-based application called Wi-Fi Designer, only available to Cambium Networks partners. It gives you a nice swag on that predictive to be able to visualize the coverage you'll get from an AP. But that's not all, right? That's not all. One of the things I've always done in network deployments is do a predictive. It's a nice way to get a swag for how things are going to cover, but then go out and do a site survey and actually do some measurements on a real network to see if you can be able to model the physical environment and the impacts that has, and make sure that that's matching your predictive design. All right, Wi-Fi 6E. So VLP 14 dBm, LPI starts at 18 dBm, which is 5 dBm per megahertz, and it maintains that, and it goes from 18 up to 27 dBm on a 160 megahertz channel. So I've read, however, in the IEEE standard, I've read 30 dBm for LPI. So is it 27 or is it 30?
Well, you got to double your channel again. You got to go up to 320 to get you that full 30, right?
Okay.
So, which currently, what 160 is where we're stopping at.
Okay.
In the 8X standard.
So there's some room to grow.
There's room to grow.
Yeah.
And as you know, if it's there, manufacturers will try to push, right?
Yeah.
So I mean, we may get a 320 megahertz channel before it's all said and done out of this AX. Just because somebody says, "Hey, I could do it," and I'm going to do it.
Yeah, and I think I think there's going to be a lot of pressure to enable that 320 megahertz band. Another pressure point that the FCC is considering, and other regulatory domains are considering, is increasing the LPI from 5 dBm per megahertz up to 8. Now, they have not ruled on that. There is no decision made, but that is a request that's been made by the market, and so that would also give us another 3 dB boost, which would again help dramatically in these LPI network deployments. Okay, Mitch. So we've discussed the 3 classes of Wi-Fi 6: VLP, LPI, and SP. We spent a lot of time talking about LPI, and I think for very good reason, right? For very good reason, because the rules around LPI, it's license free. You have access to it. It's 1200 megahertz, very, very popular for LPI deployments. But I think I asked the wrong question, or I misled you on my question. So I'm going to ask you again. When we talk about LPI and those abilities of the signal to noise ratio to be constant from 20 megahertz to 40 to 80 up to 160, the same exact SNR at each step, leads us to that 160 megahertz wide channel. So how many channels can we get in 1200 megahertz if each channel is 160 megahertz? That sounds like a math problem, doesn't it? If you're given 1200 megahertz of bandwidth, how many 160 megahertz non-overlapping channels can we get?
Oh, I heard my second grade teacher in that question. Basically, you get 7. You get 7 160 megahertz channels in that area, and if you get double that in for the 80 gigahertz. So
okay, good. So if one train is leaving from Chicago at 2 a.m. and another train is leaving from New York at 3 a.m., where will they meet? No, forget it. All right, we won't go into that math. All right.
They'll never meet.
They'll never meet. That's good. Your teacher won't like that one. So now the third class that we talk about is SP, standard power, SP class. Now these rules apply. The SP class is the one we're probably most familiar with, because that's up to 36 dBm. So that's some power levels that are very familiar to us. But in order to use that, we need to use something called AFC, automatic frequency control. And so we talked about that in a previous webcast. But let's summarize that a little bit here. Mitch, what is an AFC system going to do? Why does an AFC system? What's the purpose of an AFC system? First of all, why is it there?
Well, the purpose of the AFC system. Oh, sorry. Go on.
And answer one more question. So why is it there? And tell me why it's better. Why is it better than what we're doing today with 5 gigahertz DFS? 2 questions.
Okay, 2 questions. So first, we'll start with why, right? Well, it's not like the 6 gigahertz is not being used by somebody. I mean, in Wi-Fi, it's a greenfield, but in use in general, it's not. It's used for long haul point to point. It's used for streaming in television from mobile locations back to the main station, and it's used in the satellite from Earth stations to up to the satellite. So I mean, it's already used by something, right? These people have paid for licenses, they paid for the use of it. So we've got to kind of help coordinate, because I mean, they paid for it, they deserve just the same right as us to use it. So now we have, automatic frequency control. And this automatic frequency control says, hey, I know you want to in our case of our Wi-Fi, right? I know you want to operate on this channel, but there's an incumbent in this geolocation, right? Because FCC does things by location, by lat and long, so that they know where each transmitter is at. It says, well, you can't operate on this station. You got to move over to here, right? So there's a little bit, not a little bit, there's a lot of coordination in the sense of allowing the incumbents to freely transmit and not be interfered with, as well as our network to be freely transmitted and not to be interfered with, right? Because we would be interfering with each other if we didn't have this. And so that's really what that AFC provides us. And you kind of brought up that DFS channel, right? In the 5 gigahertz, they opened up some more band, but that was also utilized. But we didn't really. We kind of worked on an honor system, right? So if I heard somebody else transmit on that, then I need to move. And really, one of the big utilizers of the DFS channel is our the weather radar, the Doppler radar, and some of the radar that's used at the airports. So if we heard that, they weren't going to move. We're going to move, right? The Wi-Fi is going to move. So we moved, which meant that the clients got upset because now we got to go find a new channel to be on with you so we could keep talking, right? There was really, like I said, it was an honor system. I promised I will move if I hear that interference, right? Whereas this one is, no, I'm not even going to let you operate there if there's a possibility of interference. So it's a much more coordinated effort as opposed to the honor system, and it will create a more stable network.
I like that. Another thing about DFS that was a failure from a. I always worked at a hardware vendor, but I also did lots of field deployments. The challenges in deploying that technology is the access point now has to listen to these pulses of radar that are happening in microseconds, which is not a normal time frame that an access point deals with. So it has to deal with these very, very small micro pulses of radar. It has to detect it, try to determine that that's a radar signal. And then it has to do that scanning for 60 seconds, a whole full minute per channel before it can actually access that channel. So all of those rules led to an honor system, but also led to a lot of false triggers. Maybe it saw some radar, so it bounced off to another channel. All the clients had to move over, and maybe that channel really was clear. Maybe it was a false positive. And so it led to a lot of false triggers on radar, whether they're really there, and also a lot of missed triggers as well. Again, because of that short pulse duration of a radar signal. So it made it very difficult to actually implement DFS consistently. So I like AFC. With the AFC, as you said, it's a deterministic set system where the regulatory domain knows the geographic location of the incumbent user and just simply tells the AP what it can and can't do. It's very simple. You can use these frequencies, you can use this power level. So SP class. Now, SP class will be allowed to be used outdoors and indoors under this control of this AFC system. Outdoors, probably higher likelihood of interference, right? Because it's not going to be restricted by the building construction. So definitely when it comes to outdoor networks, SP class is going to be really needs that AFC system. It's going to be very, very important. LPI, low power indoor. The word indoor is the key word there. Literally means indoor only. LPI is no license required. You can use the entire 1200 megahertz as long, and the access points will already be programmed to obey those access rules. So LPI will be, in my opinion, the most widely used of these modes. Okay, so now we're talking about SP class now, and we spent a lot of time talking about standard power as it applies to the access point, what frequency it can use, how much power it can transmit. We've talked about that in depth. We haven't talked about the clients. So what controls the client's frequency and power level connecting to a standard power network?
I mean, it's going to connect to the AP. So basically, yeah. I'm going to broadcast about 6 dB lower. Mm-hmm. If I'm a mobile client, than what the AP is at. So therefore, the rules are kind of extended to me like QED, right? That famous math statement is like, since my AP is limited here, I have to be 6 dB lower than the power that I was transmitted to me. So therefore, I'm going to transmit at 6 dB less.
Okay, good. So that's a mobile client, like a smartphone or a tablet, laptop. What other types of clients are out there? I mean, what if somebody was deploying, say, a mesh network using standard power, or a fixed wireless broadband network using standard power class networks?
Well, now I'm a fixed device, right? So now I should be able to broadcast. I have that 6 dB limit removed because I'm fixed. I'm not moving. I have less possibility of interfering with one of the incumbents. So therefore I can operate a little bit higher power.
But you're also under, would you still be under control of AFC?
Well, yes, because I'm going to be directly attached. The idea is that I'm always attached to the network, and I'm not roaming from this AP to that AP or whatever. I'm going to be talking to the same guy each and every time. Well, I mean, relatively, right? Mesh is kind of a self-healing, but if I move from one of my mesh points to the next mesh point, then yeah, I'm going to have a change. But really, I didn't physically move. I just changed who I was talking to.
Yeah, so access points and fixed clients connected to those access points could be mesh nodes or a fixed client device. They're all under AFC control, but the mobile clients that connect to any of those access points are 6 dB lower. Is that right? Did I get it right?
Yep.
Okay, good, excellent. So now with these three classes, and in the United States, the US FCC, we only have LPI and SP because VLP has not been allowed yet, has not been ruled on yet for the US FCC. But if we look at this LPI and SP, we also mentioned AFC systems are not available yet. So, boy, what are people going to have to do? Now, Cambium, we are a manufacturer, a designer of wireless systems, and we see the same problem. We see a problem here where people are going to buy an access point and expect to utilize this SP class of transmit power, and they're not going to be able to do it because that AFC system is not yet approved and built and commercially available. The FCC has not issued rulings on that yet. So what do? Do they just buy an AP today? Why don't you walk us through a little bit what Cambium is doing in terms of technology to help people sort of bridge these what we do today and what we're going to be able to do tomorrow with Wi-Fi 6E. What kind of bridges can we build in technology?
I mean, we program these chips, right? I mean, a lot of chips have wide ranges, so we have software-defined capabilities. So we can actually do a software-defined radio to allow us to have that ability in the future to enable that frequency band when it's available, right? Okay. Until then, we easily say, okay, you're a 5 gigahertz today. Well, we can make you a 6 gigahertz tomorrow because it's a software-defined radio. Some of our APs kind of do that now. We don't need that 2.4. I need a 5 gig, so I want to do 2 5 gig radios as opposed to a 2.4 and a 5 gig, right? Because I mean, we have that capability, and we're already using software defined. So we just said, hey, let's reutilize this in another way to future proof, in the sense that, hey, we know that we're limited right now because we don't have the AFC.
Yeah, so software-defined radio is really a nice way then to build in some investment protection, quite frankly, because if you buy an access point today, Wi-Fi 6E, and you think, well, I want to use it the same way I always used it, I want to use standard power, but standard power is not available, that investment is now wasted. It's wasted until some point in the future an AFC system becomes available that you can start to use. So the way Cambium is doing the SDR in our Wi-Fi 6E products, in fact, all of our Wi-Fi 6E APs that are being released and will be released in 2022 will have this SDR capability for exactly that reason, because it enables you to adapt your network designs according to two factors. And you and I have talked quite a bit about the impact of the device type on the network topology. And so what if your network doesn't have a lot of Wi-Fi 6E clients in it? And then all of a sudden, at some point in the future, it does. So you need to have that ability to react when your ecosystem of devices requires the 6 gigahertz network, and you need to have the ability to really migrate your design methodology from what you do today in 5 gigahertz to what we're going to do tomorrow in 6 gigahertz, whether it's LPI or SP. So that's where Cambium's software-defined radio technology is really going to help. And one other thing, Mitch, I'll tell you about, because I've been talking to some of the other engineers about this, and so I'll give you a little clue on some things, and the listeners, this webcast, hearing it probably too for the first time. We're also building in some automation tools into our 6 gigahertz design migration. So building in some migration tools that will actually monitor the network and actually tell you when you have, how many you have, and what percentage of devices support Wi-Fi 6E, support the 6 gigahertz band, even if you're not deployed yet, even if you have not actually deployed the 6 gigahertz network. This will tell you if the clients in your network are capable of using the 6 gigahertz and give you a recommendation as to at what point you should consider migrating that network over, flipping that software switch over to use the 6 gigahertz band. And that's going to be a nice migration tool.
That is, sorry, go on.
No, it's a good tool, isn't it?
Yeah, it's a great tool. I mean, how many times do you have networking equipment that tell you, hey, you can upgrade me?
Yeah, with the flip of a switch.
With a flip of a switch, it's like,
yeah.
Oh wow, that's amazing, right? That's ingenious. I'll just say that word right there, ingenious.
It's one of those things. We thought about it a lot. The engineers put a lot of thought into how do we make this process easy for people to do. Because quite frankly, once you deploy the network, you don't necessarily know all the clients, and if you say you're an IT administrator of a school district, I mean, you don't know what types of devices are in that school. It could be higher education or K through 12. It's a significant amount of work to try to figure out and survey people and ask them, what kind of devices do you have? And then you make a decision, well, do I have enough devices to migrate to 6 or not? It's hard to find that trigger point, the right point in the future when you need to upgrade. So that's why we added the additional intelligence into the network architecture to actually assist in this migration, to actually tell you, this is the number you have today. It's not a problem yet. This is the number you're going to have in the future, or maybe you're there now, and this is when we recommend the network will be improved if you upgrade to 6 gigahertz. So we like that tool, that migration tool for 6 gigahertz and Wi-Fi 6E. So Cambium is including that in our Wi-Fi 6E product portfolio that we're releasing now, and the rest of the products in 2022. Well, Mitch, thank you very much for joining us. We've talked quite a bit about Wi-Fi 6E. We've talked about the benefits of this technology, why it exists. We've spent a lot of time talking about the 3 classes of Wi-Fi 6E: the VLP, the LPI, and the SP, the different rules for each one, and what the benefits and advantages are of these different Wi-Fi classes. So thank you very much for joining us. And as we get more experience with Wi-Fi 6E and some deployments, I hope that you will join us again in the future, and we can talk about some real examples and some people that have done those migrations to 6 gigahertz.
Would love to.
All right. Thank you very much.
Thank you.